Okay, I propose we can start with the webinar. Good morning or good evening, everyone. Depends where are you connecting from. A few words about me. My name is Mateusz. I am a structural engineer here at SDC Verifier, and I will be your today's host on the webinar regarding the weld strength and buckling checks in offshore oil and gas industry. So let's start. Today's agenda looks like this. So we will start by explaining why weld and buckling checks are very important in offshore design. And we will mention a few major standards that are used for those checks. And then we will show a few typical welded connections that are often met in the offshore structures. We will show how the weld checks are treated in different standards and what are the usual issues that engineers face whenever trying to perform weld strength checks. Then we will switch and talk a little bit about the buckling, different buckling modes, and so on. And once again, we will show how different standards approach these buckling verifications, and also what are the challenges that engineers face on daily basis. And finally, after describing all of these issues, we are going to see how SDC Verifier helps you with that, how it makes your life easier, reduces your time, basically how it automates weld and buckling checks inside ANSYS, FEMAP, SimCenter 3D, but mainly we will focus on our standalone version. And at the end, if the time allows, I will try to briefly walk through generating the reports in SDC Verifier, which is obviously a huge time saver, and it reduces manual work a lot. Okay, so a few words about SDC Verifier. The company was founded in 1998 by Wouter van den Bos. So as you can see, we have 27 years of engineering experience. Currently, we have 3 offices, and this is Haarlem, Krakow, and Lviv. And our headquarters are currently in the Netherlands. Our company is divided into 2 main departments, which is the development department, where our developers basically develop the softwares that we are selling. And then there is the second department, which is the engineering department, where we do consultancy projects. And for those projects, we use the software that is basically developed by our team. So not only we test the software, we also try to come up with the improvements. We find the bugs and basically try to make the life as easy as it can be. As you can see, our team consists of over 40 people. We completed over 300 consultancy projects, and in terms of the software, we have over 1,000 happy users. Okay, so starting with the topic of today's webinar, the importance of weld and buckling checks. So as you know, offshore structures operate in one of the hardest environments. So they have to deal with constant cyclic loading, some saltwater corrosion, fatigue, extreme weathers, and sometimes even accident like ship impact can occur. So in such conditions, weld are often the weakest link if they are not properly assessed. So a single weld failure can cause an entire joint or even an entire structural component to fail. And because welds carry high local stresses and are sensitive to fabrication quality, it is important to basically conduct checks according to standards. Similarly, buckling is one of the failure modes in many offshore structures. Slender members, stiffened panels, legs of jackets, and so on. All of these are very sensitive to buckling. What makes buckling also particularly challenging is that it doesn't announce itself gradually, but when it occurs, this is a sudden change of deformation, and it can be really catastrophic and can lead to even failure of entire structure. So that's why the buckling checks are essential. And also what I didn't mention, that even though that the structure can be well within the yield limit, and the buckling can still occur, so it has to be properly assessed. To ensure and to meet these requirements, basically, there are several major design standards that we need to follow. And each one of those has its own rules, its own guidelines, and they have some differences. So as you can see here, I showed some standards like ABS, DNV, Lloyd, BV, API, and NORSOC. And these are all offshore related standards. ABS, we have implemented ABS in SDC, and it is related to plate buckling. In our library, we also have DNV for plate buckling, and we also have Weld check for DNV. Lloyd's is also for plate buckling, BV also plate buckling. API is also plate buckling, and NORSOC is beam buckling. So even though all of these standards have the same goal, so it's basically to ensure the structural safety, they have some differences. For example, how the stresses are extracted from the model, the different load combinations can be used when verifying. Different weld and buckling formulas can be used, different safety factors, partial safety factors, different allowable stress margins, and so on. Coming up next, here I would like to show the typical welded connections that are used in offshore structures. And starting with tubular joints, these are probably the most characteristic for jacket type offshore platforms. And they are used to connect braces to chords. And these are usually the main load carrying components in a structure. And their geometry can be often quite complex. On this bottom left picture, you can see we have tubular joint T-type, the middle one is K-type, and the last one is Y-type. And the next picture to the right, this is T-joint in real life. The next group, this is a pile to sleeve connection. These are typically used in foundation systems where a sleeve is welded to jacket's leg, and later it is connected to pile that is driven to the bottom of the sea. And these connections transfer very large loads, so this is also important that they withstand those loads safely. And finally, we have the stiffener to plate connections. which you will find on decks and stiffnet panels, for example. Even though those components are usually not as loaded as the, for example, tubular joints, there are still important to check, since there can be a lot of them in your model. Coming up next, we will discuss some common issues that you face when dealing with the weld checks. And the first issue would be relying on manual formulas and spreadsheets. And this approach is still used by many companies even today. So after you calculate your model, we obtain some stresses, some forces from the FEA analysis, but most design standards still require some additional intermediate calculations before you get the final utilization factor and an answer to your question whether the component is safe or not. So this means that engineers often need to extract some forces, some results, plug them into some Excel sheets, and basically calculate all the next parameters. And with this many steps, it's very easy to make a mistake, either by inputting the wrong values or by having a mistake in your formula somewhere in the spreadsheets. And not only it's easy to make a mistake, but it's also very time consuming. And in SDC, how it is solved, all the formulas are already implemented. You cannot change them, but you can preview how everything is calculated. So you can, for example, see here that for the NV weld strength, we have total number of 15 checks, and you can preview all of them and see what parameters basically are used for what calculation. And what is worth mentioning here also, that if you have your own approach of checking some welds or plate buckling or whatever, you can also create your own custom standards inside of SDC, or you can also modify the existing standards. So you can copy the standard and basically adjust some formulas inside of it according to your preferences. The next issue is the correct application of some loads, such as environmental loads, in your FEA model. So, as you know, offshore structures are exposed to variety of complex loads, such as wind load, buoyancy load, and wave loads. And in most FEA tools, applying those loads can be not only hard, but also time consuming. But in SDC, we have a special module which makes applying these loads very easy and very fast with a few inputs. So for wind load, all you need to do is basically define the drag coefficients based on your standards and define the direction of the wind and the pressure. It can be a constant with the height, or it can increase. For buoyancy load, you need to specify the waterline height. And for wave load, you have a few more parameters. For example, the distance between the sea level and bottom of the sea, the current speed, and the height of the wave, the time interval between the waves, and so on and so on. And for example, we also have a quite extensive documentation. So if you want to read more about those stuff, you can simply go deeper into our documentation, where you can find all the descriptions about either applying those loads or other functionalities of SDC, and even how to correctly implement some standards. And the next issue is that load combinations are time consuming to analyze and to post-process results. And here I will play a quick video. So as you can see over here, we have a crane with its trolley that is traveling across the girder. So as you can see, due to the girder's length and to analyze the structure in detail, it is required to take some more additional positions of the trolley. But doing that for one load combination, you already have 10 load sets, and if you were to analyze, for example, a trolley traveling in different directions, then you can see that those load combinations can quickly add up, and you can easily end up with hundreds of load cases and sometimes even thousands of them. And not only creating them is time consuming, but analyzing them one by one and post-processing the results can be very time consuming and basically hard. So what SDC proposed to do, our approach is that all individual loads are calculated only once. So what is individual load? Individual load is a combination of one FEM load with one set of constraints. And then the load combinations are created linearly without recalculating the model. And you can also obviously use your correct factors that are defined by standard. So for each load set, you take the results from the individual loads without the need to basically recalculate the entire model. And also what we usually do, what can be done, you can prepare your load sets in Excel sheet and then just copy and paste them into SDC, or you can directly prepare them in SDC. Whatever is your preference, you can choose. The next issue that engineers face is that weld checks are not performed on finite elements directly. So what that means is that weld checks should be performed on structural members. So basically what engineer would need to do, he needs to identify all the welds in the model, where they are, what are their geometric dimensions. So it would be length, what is the thickness of the welded plates, and so on and so on. And here SDC comes in handy with our recognition tool, which is weld recognition. It very quickly, with one click, recognizes all the welds in the model. As you can see on the right picture, all the welds are highlighted, and it automatically reads the dimensions. So it automatically reads the weld length and the thickness of the welded plates. Also, what is required for the weld strength analysis, this is the weld type and the dimensions of the weld. So if you have many dimensions, many welds, you need to apply all of the dimensions manually to each weld, which can not only be very time consuming, but it's easy to make a mistake. But I will show later in SDC how it is solved and how you can quickly assign those dimensions. When talking about welds, the other issue is that incorrect stress orientations might be used, and basically you can extract the wrong results for your formulas. So as you can see on the bottom right picture, each element has its own coordinate system, and based on that coordinate system, you can have your normal and shear stress component in different directions, which is incorrect because for a weld, for a structural member, the coordinate system should be the same for all elements. So the x-axis for each element should be along the weld, and the y-axis should be in the perpendicular direction. And SDC basically does that automatically. It transforms all the coordinate system in a way that they are, as I just said, x is along the weld and y is perpendicular to it. And also for weld strength checks, 4 points, 4 stresses are calculated. This is the T1, T2, B1, and B2 point. This lay on the throat section. That would be it for now when talking about weld checks. Let's go to the backlink right now. So what is backlink? Backlink, as we said, is one of the failure modes. It is a sudden loss of stability of a structural component due to the exceeding of the critical compression force. And as I also mentioned before, even though that your structure might be well within the allowable limits when it comes to the yield stresses, it can still fail due to buckling. So it is important to check. The critical compression force can be described with the use of the Euler's formula. And based on this formula, you can see that the buckling does not depend on the strength of the component, but rather on its stability and stiffness. So as you can also see, it depends on the way, on the boundary conditions, so how the beam is supported. We can also say that there are two types of buckling. This is global buckling, and there is local buckling. So global buckling is the loss of stability of entire structural member, and this can lead to catastrophic scenarios where basically a structure can collapse, and the consequences can be very bad. And local buckling, this is the smaller portion of a model undergoes buckling. So, for example, a stiffener somewhere inside a beam, and yeah. What are the common issues when talking about panel buckling? These are basically what I mentioned before. So it's dealing with the manual spreadsheets, its load combinations, and so on and so on. But when talking about the recognitions, same as here, the buckling checks are not performed on the finite elements directly, but they are performed on the panels. So basically, once again, similarly to welds, instead of manually finding all of those panels in your FEA model, extracting all the geometrical dimensions such as length and width, you can use our recognition tool, which is panel recognition, which will help you to find all the sections, all the panels, plates, and stiffeners inside the model. And it will also automatically extract all of the dimensions of it. I will show this briefly in the later part of this webinar. We just showed panel backlink, but it's also possible to perform the beam backlink. And for beam backlink, what you need to do is recognize the beam elements. And for that, another recognition tool comes in handy, which is the beam members recognition. And to maybe summarize all of those challenges that engineers face when working with those checks. First of all, yeah, as we said, this is working with manual calculations. And yeah, as we said, many standards require intermediate calculations, and doing this in spreadsheets can easily lead to mistakes. Another issue can be extracting the correct stresses from the FEA model, because if you pull stresses from the wrong element, wrong side, or wrong coordinate system, the entire verification can be invalid, basically. Engineers also need to manage a huge number of load cases and load combinations. Offshore structures can often have, as we said, hundreds of thousands different loading scenarios, and analyzing each one of them is very time consuming. Then identifying the governing loads. So it's also important to know which load scenarios are crucial for your structures, which cause the highest stresses, highest utilization factors, and so on. There are also challenges in accurately representing the geometry, whether you should model the welds or not, how to take them into account. And another issue is, as we also discussed, this is the risk of incorrect member or weld dimensions due to manual input. Another one, this is the complexity of correctly applying loads. So as we explain, especially the environmental loads, such as wind, waves, and buoyancy. Then another challenge, this is ensuring consistency across team and tools. So when you have an offshore structure, it often has to be not only checked by one design code, for example, backlink, but often it has to meet standards like strength, static stress check, fatigue, weld check, backlink check, and so on and so on. And for this purpose, if you have to jump between different softwares or different spreadsheets, it can be not only annoying, but you can also make mistakes, lose some data, and so on. It's better to work within one environment, and we will show it later. On top of that, engineers have to process a large amount of FEA data, and it is sometimes hard when working with many load combinations and a huge model. It's often basically impossible to not miss any area with overshoots. But we also have a solution for this, which we will explain later on. And finally, we need to produce nice, transparent reports for the client. And this often requires preparing hundreds of plots of tables. And this is another source of potential errors and also a very time-consuming process. So yeah, what is SDC Verifier? Yeah, SDC Verifier is basically a solution to all of those errors that we just explained. So SDC Verifier is an FEA software, and it can work in different ways. We have the standalone version, in which you can basically perform everything, starting from preparing the geometry to meshing to analyzing and doing all of those parts, as you can see, the combination, recognition, checks, optimization, and reporting. And we also have another type of application which works as an extension to already popular FEA softwares such as ANSYS, such as FEMAP, and such as SimCenter 3D. So I will maybe explain it a bit later, but let's focus on this graph right now. So based on years of experience, we came up with this workflow how to basically approach each project. So we start by preparing our model, obviously, and simulating it. And with that, we received like initial stresses, forces, deformations, and so on, which will be later required for our checks. And then we can proceed with preparing the load combinations. We can take into account different loads, different directions, and obviously set different partial safety factors and factors depending on the standard requirements that we are using. Then the next step, and this is the recognition tools. So depending on the checks that we are going to perform, whether it's beam buckling check, plate buckling check, or weld recognition, weld strength check, we need to recognize those structural members. And then after recognition, we start by setting up the standards check. And as you can see, currently we have over 50 industry standards, and this library keeps expanding all the time. The next module is optimization. So whenever your results do not match the standards requirement, for example, the plate buckles, the beam buckles, the weld is also not within the allowable limits, you can optimize those parameters to make sure that you are well within the safe margin. And after all of this is done, then you can proceed with preparing a report. And here for the reporting, we already have some predefined templates, which can save you a lot of time. But I will maybe also talk about this slightly later. What is also important here, you can see these arrows around each of those components. What that means basically is whenever you prepare some report, you have everything set up, and suddenly you have to do some design optimization, some update in the model. You don't need to basically repeat each of these steps again. You simply just update your model, reanalyze it, and all the load combinations stay the same, all the recognition is the same, all the checks, definition, everything. You can simply just open your report, click regenerate, and everything that you just set up, it will be the same report, but with different outcomes. Also, we have a new software, which is SDC SAM. It works as a web platform where you can maintain your assets, but I think I will also talk about it a bit later. So, as I mentioned, we have our SDC Verifier standalone version. This is all-in-one solution. So as mentioned, you can start by preparing geometry here, by meshing your model, applying all the loads, constraints, and so on and so on, and basically analyzing the model. And after you are done with the analyzing, you can go over all of those steps as shown before. So we can prepare the load combinations, do the recognitions, set up the checks, check the results from those standards, and then we can do some optimization and prepare the reports. What is also worth mentioning here that you can import some CAD models, 3D geometry from your CAD software. So you can import a model over here, clean up the geometry, do some mid-surfacing or extracting center lines together with profiles and so on and so on. So converting your 3D models from CAD and making it basically suitable for FEA analysis. This is possible and very easy with an SDC verifier. And as mentioned, the second type of application, these are the extensions to already popular CIA softwares. So in this case, it's ANSYS. And how it works is you basically have your model in ANSYS, all the loads, all the constraints, everything is defined directly in ANSYS, and your results and solutions are also in ANSYS. Then you connect the SDC verifier in this example for ANSYS to the model. It reads all the results, so all the necessary stresses, all the necessary forces, displacements, and so on. And you are basically ready to post-process those results. So you can start by creating, as mentioned before, those load combinations, and then recognizing all of those structural elements and predefining the standards, doing optimizations, and automatic reporting. The idea is basically the same for SimCenter 3D, and you can do the same for FEMAP. So you have your model in FEMAP, and you connect your SDC, read the results, and then perform the rest in SDC for FEMAP. As mentioned before, we have a few recognition tools in SDC. We already mentioned a few of them, but there are also more. So we also have a joint/connection finder in SDC, which is used for some joint checks. We have, as discussed, a beam member finder, which is used for beam buckling checks. Then we have a panel finder recognition, which is used for panel buckling. We have weld finders, which is used for weld checks and also important in fatigue assessments. And lastly, we have beam section finders. Here I created a quick video on how the recognition basically looks. So as you can see, with one click, all the welds in the model have been recognized. You can check the tensile strength, yield strength of all of those welds, and you can even preview them. You can see how they look in the model. They can be recognized between plate elements, between solid elements, and even between connection of plate and beam elements. Another important thing, as we mentioned, for weld strength check, this is setting up the weld dimensions. And as you can see, over here we have a list of all weld parts and the dimensions that were written from the model. So we have length of the beams of the welds, we have the thickness of welded part, and we can even see that the rotation of coordinate system to take into account this weld coordinate system as we described before. You can always change those dimensions and set your own. And on the bottom right corner, you can see that you can define also the weld types. So you can choose between double full penetration, double partial penetration, a double fillet, and single fillet welds. And for each one of them, you have a corresponding sketch showing the dimensions. So when choosing each weld, you can either set the dimensions based on, for example, weld like horizontal dimension or vertical dimensions. For penetration welds, you need to input penetration depth and so on and so on. And what you can also do is specify the weld throat, as I did over here. So you can specify the weld throat to be half of the thickness of the welded plate. And this welded plate thickness is already extracted from the FEA model. So basically, all the welds right now have a defined dimension. I click OK. OK, and basically the welds are prepared for weld checking. And next, coming up next, also quick video. It shows how to perform the panel checking, panel recognition, I mean. Also with one click, you can see that on the left side we have our sections recognized, and on the right side you have a list of panels, plates, and stiffeners that belong to those sections. Together with all of those components, you can see the dimensions that were written. So what is the length, what is the width, and even the directions. You can also plot the sections. So as you can see, X sections look like this. We can plot Y section, looks like this. And we can plot all the panels that were recognized in the model and that will be used in the panel backlink check. Okay. Coming up next, as we already mentioned, our current library consists of over 50 engineering standards. They are grouped between different categories. So we have fatigue checks, we have beam backlink checks, plate backlink checks, and we have bolt checks, static stress check, weld strength, and so on and so on. So you can choose something for yourself. Quick comparison on how different standards treat weld strength. And in general, the ideas are the same. There can be obviously some differences since some standards rely more on experimental data, and some combine experimental data together with theory. And on top of that, as you can see, different standards can specify different load combination, different safety factors, different allowable stress limits, and so on and so on. So as you can see here, a quick comparison between DNV and Eurocode weld check. Even though both of them are checking the von Mises stresses and normal stresses, you can see that the allowable stress is a bit different, and also the correlation factors are slightly different in both of those standards. And this results in different outcomes when performing the analysis. So as you can see, I checked the results for both of these standards, and on the first plots from the left side, I plotted the total utilization factors, and as you can see, for DNV we received smaller value, which is 4.12, and for Eurocode it is 5.15. So it is more, this is the higher value, more conservative result. And what is also nice, what is shown on the right pictures, you might look at the left outcomes and say that, okay, the welds are, let's say, blue, so we are well within the allowable limits, so no need to worry, but that is not the case. To make sure you do not miss any critical area, we have a peak finder tool, which basically shows the elements with results that match your criteria. And in this criteria, in this case, the criteria was the value of utilization factor exceeding the value of 1. So all the elements that did not pass the check. And you can nicely see that they are in the common area and that they are indeed some overshoots. And this I will skip since we are running out of time slightly. Then I also compared results for backlink checks. Once again, DNV and Eurocode. And you can see that this time for DNV, we received a maximum value of 1.40, and for Eurocode, it is 1.34. And on the right side, you can see the areas of the overshoots. This I will also skip. Okay, another module, as we briefly said before, this is the optimization. So whenever your, let's say, plate buckles, beam buckles, or weld do not pass the weld strength check, you can basically optimize it to match the criteria. And for example, for beams, we have a library of already prepared cross sections that can be taken and analyzed to match the standard requirements. And it is also important that it can be optimized in a way to match standards requirements, but also if you are well within the allowable limit, to not over design the construction, you can also basically decrease the sizes to decrease the weight of the structure and to save on some material costs. So it can be in both ways. And then lastly, basically, this is the automatic reporting. So here, as I mentioned, we already have some predefined templates that you can generate. So we have 3 templates. The first one is a model setup report. The model setup report consists of all information regarding the model. So basically, what are the materials, what are the masses, weights, what are the properties used, all the FEM loads, all the constraints, beam releases, and so on and so forth. Then we have a result report, which consists of already predefined tables and plots for every individual load, for every load combination, for every load group. Of course, you can add your custom stuff. You can add custom plots from checks. custom views, and so on and so on. So it's highly customizable. And we have also the third template, which is a full report. So it's basically a combination of both of those. And I also forgot to mention that in a result report, you also have a chapter that is focused on the standard. What are the checks in the standard? What are the parameters, all the inputs, classifications, all the formulas for the checks, and so on and so on. And as you can see, all of them can be exported to PDF, to Word document, and to PowerPoint. A few words about SDC Sum. This is a web-based solution. What is it for? It is basically for tracking your assets and maintaining their condition. So what you basically do, you import your results to the web, and you can preview what is the condition of this structure. You can preview the general condition or a condition of smaller components. And this model also, you can preview all the welds, all the panels, all the beams that were recognized. So basically you have all the results that were calculated within your web. It also shows you the potential areas that are in critical condition. You can track when you need to perform inspections, and so on and so on. So coming to an end, thanks to feedback from our customers, thanks to years of experience, we calculated that thanks to SDC, you can save up to 80% of the time for modeling, for analysis, and for creating reports. So instead of wasting your time and preparing some plots, some tables, and so on, you can do some more challenging actual engineering work rather than just preparing plots. So the benefits in a nutshell, once again, is verification is directly in popular CIA softwares. So as we said, you can connect to ANSYS, you can connect to FEMAP, you can connect to SimCenter 3D. But besides that, we also have our own all-in-one solution, which we recommend to everyone. Then we can perform all the necessary checks to ensure the crane's structural safety. So we can perform bolt checks, fatigue checks, backlink checks, strength checks, and so on and so on. Then, when talking about the checks, we have many popular codes, over 50 of them at the moment, and this number continuously increases. The consistent calculations, as we mentioned, whenever there are some updates, then you simply recalculate the model and can regenerate entire documentation. And entire documentation can be quite automatic because, yeah, as nobody likes writing reports manually, right? I think this is a great conclusion. Few last slides. SDC Verifier, yeah, we have over 200 customers around the world. Some of the logos you might recognize. And in offshore and maritime, these are our clients. Lastly, I would like to invite you to our YouTube channel, where you can find any updates regarding our software, our releases, new functionalities, and you can also find many educational content over here. So, for example, webinars such as this, and also tutorials how to perform certain checks, how to use certain functionality within our softwares. Okay, that would be it from my side. I hope you found this webinar informative. In case you have any questions, feel free to ask them on the chat. We still have 4 minutes, so we can answer them. And if you don't have any questions so far, or you might have later on, feel free to send a questions either on my email, which is the first one, or on the second email, which is the support email. I will bring the chat. Okay. I see a question. Is it possible to recognize connection of two plates as weld if that connection made with RB2 elements? No, unfortunately not. They have to be connected with a node. So no. My question is about how SDC collects stresses from model. Does SDC use an average stress of the element instead of using average stress information, and why? You can use both of those, actually, I believe. During ship hull preprocessing, the plates are shared topology. How is the Weld model incorporated in this case? How Weld Weld recognition works in SDC is basically you need to have a separate properties for both plates. So if you have they where they share topology, the elements need to be from different properties, basically. And this way it will recognize unweld in this area. So if you have two surfaces and one is meshed with property 1, second one is meshed with property 2, then as this will recognize a weld here, and even if it does not recognize because you use the same, you can still manually add this weld later on in the weld recognition. I hope that answers your question. No. Topology should be shared to make sure that the nodes are coincident. But they need to have different properties in order to recognize weld. Hey, I use SDC 2024, and I was wondering if a newer version is DNVC 201 later standard, because in my version I see only the 2010. I can even show you right now. I'm using the 2025 R21 version, and we have such DNV standards. So for C201 plate backlink, the newest is from 2010 that we have. My second question is bolt connection. Is it possible to recognize? The bolt connection, we don't have recognition tools for bolts, but yeah, we can perform the checks on bolts if they are modeled with 1D elements, basically. So you need to prepare a certain selection of elements and that you want to do the bolt checks on. We have many tutorials about this on our YouTube channel, so you can also go there and browse. For backlink calculation, there are mesh results and plate average results. Which one is generally accepted but by classification societies? I think that there are both, honestly. And I remember I was even checking this in one of the standards. But this detailed question, maybe I am not an expert to answer honestly, but feel free to drop a question on our support, and our experts will definitely reach out to you. Thank you for the feedback, everyone. I will still wait in case someone has any questions. No problem. You are welcome. If there are no questions, then thank you so much, everyone, for listening to. It was my first webinar, so I hope you enjoyed it. You learned something, and I wish you a happy Christmas, a happy New Year, and stay tuned for more webinars like this. There is another question. When I work on the ship section structure, I create large surface and the intersecting smaller surfaces are connected using shared topology. In this case, should the large surface be manually splitted? No, the shared topology is fine if it's used. If this softwares, if these surfaces are not combined into one body in space claim or whatever geometrical interface you use within ANSYS, if they are not combined into one body and these are separate bodies, but they share the topology, then it will recognize welds between them. Was the webinar recorded? Honestly, I am not sure. I think my colleagues were recording this, and I think they should. Thank you, Vitor. Have a good weekend as well. Thank you, Wojciech. Yes, so the webinar was recorded, and I believe it will be sooner or later uploaded to our YouTube channel. No problem, no problem. Thank you everyone. Okay, so if there are no questions, then I propose to end the webinar. And thank you so much once again for staying and listening. So have a nice evening, everyone.